Hey, welcome back to numerical analysis. So I took a hiatus from doing numerical analysis just so I can catch up in my tomography class. But yeah, last time we left off, we talked about numerical differentiation. And so in order to get a whole bunch of numerical differentiation formulas, we actually used our polynomial interpolation theorems, and then we used the remainder theorem there in order to get sort of a qualitative idea or a quantitative idea of how good of an approximation we're going to be getting based on various formulas. We found that using symmetric differences was better than using sort of lopsided differences, and yeah, so we actually got some decent conversion rates. Next, we want to go the other direction. So we want to go from a function to its integral, and there's a whole lot of methods to this. This is actually a very heavily studied area of mathematics, and because integration comes up all the time. It comes up in the solution of differential equations. It comes up in doing development of control theory. So if you look at PID controllers, the I in there is an integral, and so basically you're trying to control a system based on its integral, its derivative, and a proportional version of itself. And so, but you need to be able to actually implement these in order to test to see if they're going to work. And in order to do that, you need to be able to perform an integral. And I mean, you guys took calculus too. I mean, you've seen integration theory pop up all over the place. I mean, basic physics is integration theory, right? I mean, I don't need to go and like justify it with like control theory even. But yeah, so the goal today is we're going to I'm going to introduce you to 4 different methods of taking an integral, maybe 3 depending on how you look at it. First, there's a naive approach, and that is using sort of left-hand rule. So you split an interval into a whole collection of uniformly spaced points, and on each one of those you multiply the width of each the distance between each of those equally spaced points, and you multiply the height of the leftmost point. Well, for you, leftmost point, you get the idea. But that's going to give you a whole bunch of rectangles, and those rectangles can be used to approximate the function. Turns out that's not actually that great of an estimate, and using the same collection of points, you can do much better using a couple other methods. There's another companion method to that. You can use the left-hand side or the right-hand side, but they give you the same result. It turns out taking the average of those two actually gives you a dramatically better result, and it's called the Trapezoid Rule. The Trapezoid Rule could also be thought of as taking a linear interpolation between 2 different endpoints, and then we'll be able to use our interpolation theory yet again in order to get a good estimate on the remainder that's going to be coming out of that. And so that's going to be the Trapezoid Rule. The Trapezoid Rule converges at a decent rate. I think it's big O H squared. I'll have to double check, and I'll put it somewhere around here. But yeah, it is not the fastest way to get at this. The faster or the stronger convergence rate that we get is going to come out of the Simpsons Rule. And so Simpsons Rule is basically you take actually 2 different intervals and you use a quadratic interpolation between this point, the middle point, and this point, and then you put those together. And then you just do that over and over again until you have the entire interval. And the coefficients there are a little bit trickier, but it's nothing too complicated. And you'll find that Simpsons Rule actually converges much faster than, say, the Trapezoid Rule. The Trapezoid Rule works really good if you have periodic functions, and so if they can be represented as sort of sine and cosine, it actually gives you exact reproduction if you have enough samples, and so that's handy. But for general purpose continuous functions, if you don't know if it's, say, a periodic function, then using Simpsons Rule is a pretty good way to go. And so I'm going to show you how we can arrive at the formulas for all of these, and also how to get remainder theorems for each of them. And so then that'll basically cover integration of continuous functions, and we'll use one lecture to talk about Gaussian quadrature and other things like that. By the way, quadrature is sort of the old school name for doing integration. when people were trying to find areas between curves or other things like that, or area underneath the curve, it would almost always be called quadrature. So if you hear me say that term a lot, I'm just saying integration. But yeah, so let's go ahead and get started, and I'll see you on the other side. So I'm gonna go ahead and see if I can record this in several sessions. I'm trying a different room in the house. This one is kind of more echoey. No, hope it doesn't get too bad with this. Got this little sound guard thing around my microphone, but it doesn't help if your room isn't well sound insulated in the first place. Anyway, so yeah, let's go ahead and get started. So here we're talking about numerical integration. And so basically the idea is that, you know, you have some sort of interval, say, yeah, that's going from, say, A to B, and over this you have some sort of curve, and you know, good old calculus, you want to integrate underneath the curve. So we have, so basically you're trying to figure out what this area is, and the way you could do this numerically is that you just take several samples, right? So you have all of these samples of your function, and this is going from, say, from x naught being equal to a, and you have x1, x2, etc., up until you get up to xn. And generally we think of these as all equally spaced. It doesn't always have to be, but it works out better for the formulas. So we're going to say that k is equal to a plus k times h, where h is equal to b minus a over n. Okay, so we want to use these samples in order to get an approximation of our integral. We'd also like to be able to quantify how good of an approximation we have. So, so one really dumb way we can do this is just to use what is called the left-hand rule, where we just use only the left-hand side of each subinterval in order to get the approximation. So, and formulaically, what we're saying is that integral from a to b of, say, f, and let's say this is f of x, of f of x dx is equal to the sum of, from I going from, say, 0 to n minus 1 of f of xi, and here we're going to multiply times h. Okay, let's see. There we go. And so ultimately, I guess I didn't really need to move that. Ultimately, what we have is that this is also written as the sum of I going from, say, 0 to n minus 1 of f of a plus ih, or kh, like what we had over here, times b minus a divided by n. And the idea is that these are all approximately equal, and if we take the limit, we would see that they actually end up converging. How do we know that they end up converging? Well, let's go ahead and take a look. So if we're taking a look at each subinterval, so here we're looking at, say, xk and xk plus 1. Ultimately, this is what our function f of x looks like, and this is what our approximation is going to look like using the left-hand rule. So this is going to be a left-hand rule. Okay, so how good are we doing? Well, let's see. We see that if this was f of xk, basically we assumed that this was going to be flat this whole time. If we want to figure out what the error is, say how far off are we when we get to this point, well, what we could do, we want to get an upper bound for all these errors. And so we're going to be looking at, say, f of, say, let's x minus f of xk. And this is what how far off we're going to be, is equal to the integral from xk up to x of f of x prime dx. And so here we're adding an assumption, and so here we're going to have the assumption of f is continuously differentiable. Right. Okay, so if we have this, then what we can see is that if we take the we're going to let m be the maximum value of f prime of t, or f prime of x, over the interval a b. And so then this tells us that we have the absolute value of f of x minus f of xk is less than or equal to m times x minus xk. Okay, and now if we go to take a look at m times xk plus 1 minus xk, that's strictly getting larger. We can put absolute values here, because x is assumed on this little tiny segment here, x is somewhere around here. Then we have this. This is less than or equal to m times h, because the difference between xk plus 1 and xk is just h. So, so then we can go ahead and we can use that in order to get some sort of estimate on how fast it's going to be converging. So let's go ahead and do that. So going on the next page. So how close is the left-hand rule? Okay, so if we go ahead and take a look, we have looking at the absolute value of the integral from from a to b of f of x times dx minus b minus a, or well, let's just say the sum of I going from 1 up to n minus 1 of f of xi times h, right? Now, what I'm going to do over here is I'm going to split this into a whole bunch of subintervals. So we're going to have the integral from xk to xk plus 1 of f of x dx. And this is going to go from I equaling, say, oops, there should have been 0 there, 0 to n minus 1. Okay, so once we do that, we're going to have this. We're looking at the sum of the integral xk to xk plus 1 of f of x dx minus f of x, sorry, should have i's here, I here, and I here, f of xi times h, and this is I going from, say, 0 to n minus 1. Okay. Just cleaning up. Okay, so we have that. Now if I use the triangle inequality, so if I move the absolute values on the inside, we increase this. So the sum of the absolute value is always going to be larger in magnitude than the sum. And so, so we're going to have this. We have the integral of xi times xi plus 1 of f of xi dx minus f of xi times h. Okay. So now I'm going to exploit the mean value theorem. So the mean value theorem for integrals says that if f is a continuous function, then there is some representative in there that you can pick such that this is true. So this is less than or equal to the sum I equal 1 to n minus 1, and I can just replace this by
xi plus 1 minus xi times f of c for some c in that interval. So here we're going to say for some c in xi to xi plus 1, we have this integral xi to xi plus 1 of f of x dx is equal to xi plus 1 minus xi times f of ci. This is the mean value theorem for integrals. This is by the continuity of f. Okay, so we have that, and now we're looking at this f of xi times h. Now here, this guy, this is equal to h, and so I can now go ahead and we have every one of these terms has an h attached to it. We can go ahead and factor that out. And so we have, this is less than or equal to h times the sum I equals 1 to n minus 1 at the absolute value of f of ci minus f of xi. Now, if you remember what we just talked about here, we said on each subinterval we can do this sort of routine and we get this bound. So for m being a bound on f prime over all of ab, we get this. So this is going to be less than or equal to the sum of h times I going from 1 to n minus 1 of m times h. Okay, double check. Yep, that's what we got. So I can pull, we have h squared times m times, oops, there's a sum over 0, sorry, keep doing that. Starting at 0 up to n minus 1. And now what I'm going to have is I have n. Okay, now n is kind of inconvenient. We would like to be able to describe this either in terms of n or in terms of h, but not both. And so what I can do is I can use it in the idea that we have h as being b minus a over n, and we can sacrifice one h to the math deities. So we get b minus a over n. This was 1h, and then times n. These cancel. It gives us m times b minus a times h, and we're done. So what can I say is that the left hand rule converges to the integral as big O of h when f is continuously differentiable. Okay, and that's a nice little like starter numerical integration starter pack. This is actually not a really great way of doing integrals. I mean, if you need to prove that something converges to something else as far as an integration routine, that's fine. But at the end of the day, we want something that's going to be faster than big O of h. Big O of h, it really isn't all that fast. And so if we use the Trapezoid Rule or the Simpsons Rule, we're going to have, I think, big O of h squared and big O of h to the fourth, respectively. And so those are going to be a lot better. The Trapezoid Rule you can actually get from using not only the left-hand rule, but the right-hand rule, where you basically replace this with a 1 and go up to n, and you take the average of those two. That gives you the Trapezoid Rule. But we're going to take a look at it in a different direction, and this is going to come from using the interpolation theory that we've come up with, and that will give us nice little error bounds that we can play with and get some good results. Okay, so we'll do that next. Let's see. So let's take a look at the Trapezoid Rule with interpolating polynomials. All right. So, I mean, Trapezoid Rule is Trapezoid Rule. I mean, it exists with or without interpolating polynomials, but we're going to show the remainder formula that we get through using the remainder formula for interpolating polynomials. And I think this is called the Newton-Cotes method. And just You'll have to double check me on that, but I'm pretty sure that's what this is. Okay, so let's go and take a look at what the trapezoid rule is. And the one that used all the mean value theorem stuff, I'll put at the end of the lecture after my closing remarks, so that you can see just how bad it gets. But the idea is that with trapezoid rule, basically you're going to be given a whole bunch of points, say F0, F1, F2, F3, F4, F5, and then another guy right here. And what you're going to do is you're going to try to approximate the solution here, or the integral, by using the integral of interpolating polynomial of just first degree, where we just basically restrict to each subinterval, and then we put the interpolation there. So it's sort of a piecewise linear interpolation. This would also be called a spline, by the way. So let's take a look at each. So let's just write out what the formula is. So the trapezoid rule is this. It is basically, it says the integral from a to b of f of x dx should be approximately equal to the sum I going from, say, 0 to n minus 1 of f of I plus 1 plus f of I divided by 2 times h. Now this this here is the average of the left-hand rule and right-hand rule, and that can be seen really because if you take this side and you take this side, the right-hand rule gives you this top one, left-hand rule gives you this bottom one, and if you take the average of those two areas, then what you end up getting is just basically the area of the triangle right here, and the rest would stay the same. So that's where that ends up coming from. Okay, so let's take a look at each individual segment and show you how you build this. So we're going to take an integral from xi to xi plus 1 of f of x dx. And in doing this, we're basically going to interpolate our function f using these endpoints fi and fi plus 1. This is at xi and xi plus 1. And so we're going to subtract what we get from the integral of the polynomial. So that interpolates there. So this is going to be a polynomial of degree 1 that interpolates these points, so P1. And that's what we get. If we take a look at the remainder formula, which is f of x minus p1 of x, remember that r1 of x is equal to f double prime xc at x, some x value, divided by 2 factorial times x minus xi and x minus xi plus 1, right? So we can go ahead and compute what the remainder would be for this individual term, and then later on we'll go and just build up the entire thing. So we have xi to xi plus 1 of r1 of x dx. If we put absolute values here, I'll now pull out the maximum value. M is maximum value of the second derivative, so over the entire interval a to b. Right. So I go ahead and take that out, and then I divide by 2 factorial. Now we're left with the integral from, say, xi to xi plus 1 of x minus xi and x minus xi plus 1. Right, and so once I compute this integral, that'll tell me exactly what the it'll tell me exactly what the integration remainder will be. So let's go ahead and take a look at that. So just off on the side in a different color so we don't get things mixed up. Integral from xi to xi plus 1 of x minus xi plus 1, that's dx. So here we can just use u substitution, so u is equal to x minus xi, and we have dv is equal to x minus xi plus 1 dx. V would be x minus xi plus 1 squared, and then times 1/2, and du would be dx, right? So this ends up being x minus xi times x minus xi plus 1 squared divided by 2, and this evaluated xi and xi plus 1, which, by the way, makes this whole thing 0, minus the integral of, say, from xi to xi plus 1 of x minus xi plus 1 squared divided by 2 dx, and this is minus x minus xi plus 1 cubed divided by 6, and evaluated at xi and xi plus 1. When we put in xi plus 1, it ends up being 0, and when we put in xi, we get h. So it's going to be h cubed over 6. So going back to this guy, so what we get then is that this is less than or equal to m divided by 2 times 6, which is 12, times h cubed. Okay, and ultimately when we add all these little pieces together, that tells us that the ultimate result will end up being h squared, because we're going to have to sacrifice one h to kill off an n that we're going to pick up. So might as well say that here. So then we're going to see is that the integral of xi to xi plus 1, so we see the absolute value of integral from a to b of f of x dx minus the sum of fi plus 1 divided by 2 times h, I going from, say, 0 to n minus 1. This, an absolute value, is less than or equal to m divided by 12 times h cubed times n. But this is the same as saying m divided by 12 times h squared times b minus a. And this is because h is equal to b minus a over n. Okay, so that gives you a big O estimate. So that means that we have a big O estimate of h squared. And here we have a big O constant of m times b minus a over 12. Okay, but I still haven't verified that this is actually what you get when you do that sort of interpolation. So let's go ahead and do that. So here, this is something that's just going to come up a bunch. So p1 of x, we might as well rewrite this as a Lagrange interpolating polynomial. So it's going to be fi of x, sorry, not fi of x, fi is a sample, fi times x minus x I plus 1 divided by xi minus xi plus 1, and then plus fi plus 1 times x minus xi divided by xi plus 1 minus xi. Okay, so now you can see when you put in xi over here, you get 1, and so over here you would get 0, right? And so then that would be left with just a sample, and when you put in xi plus 1, you get this one. So that's good, but now we need to actually integrate. So let's see what happens how we're going to integrate this. So integral from xi to xi plus 1 of x minus xi plus 1 divided by xi minus xi plus 1. And then this integral will tell us what coefficient goes on that f. So let's do this dx. Now if I go ahead and set t, if I go ahead and pick a t such that x is equal to a plus th, we can have a nice sort of adjustment. First of all, by doing that, we see that xi is equal to a plus ih, which, so t would be I, and then we see xi plus 1 would be a plus I plus 1 times h. So so then what we end up getting is this. Is the integral from I to I plus 1. We're going to have a plus th, and then this times, then we subtract off a plus I plus 1 times h. So put enough parentheses here. Okay. And then on the bottom, we end up getting minus h. Now, if we're making this change of variables, we see that dx is equal to t dt times h. So we have an h and a dt here. Okay, well, a and a cancel, and so that's nice. And then we can pull out an h, which will cancel that h on the bottom. So we end up having it minus h times the integral from I to I plus 1 of t minus I plus 1 divided by h. Sorry, not divided by h. We got rid of that. There. And this is all dt. And if I make a substitution where I replace t with t minus I, then we end up shifting the integral to being, it's going to be minus h times integral from 0 to 1 of t minus 1 dt. Okay, now I can go ahead and wrap that up. So I take the integral of that, and that's going to be minus h times, say, t squared over 2 minus t. And so we're evaluating this at 0 and 1, and did I make a mistake? I don't think I did. Nope, looks fine. All right, so I evaluate t at 0 and 1, and so I get minus h, and then at 0, everything goes away, but at 1, we're left with 1/2 minus 1, and then ultimately is minus h times minus 1/2, and so that's plus h over 2. Okay. All right, so good. So that means that when we put in our formula, this integral ends up being h over 2. So, so when we're making our trapezoid rule, we're saying that we're basically summing over all these guys, xi to xi plus 1 of p1 of x dx, I going from 0 to n minus 1. And ultimately, we know that is going to be this. Is going to be fi times the integral from xi to xi plus 1 of x minus xi plus 1 divided by xi minus xi plus 1 dx plus f2 times the integral of xi to xi plus 1 of fx minus xi, sorry, x minus xi, then we have xi plus 1 minus xi, right, dx. So what we've just shown is that this piece here integrates to h over 2. And similar calculation will get you that this guy is equal to h over 2. So we conclude then that the trapezoid rule, which is what you get when you do a piecewise linear interpolation, is that you have integral the sum of I equals 0 to n minus 1 of f of I plus 1 plus f of I divided by 2 times h. And there you go. Okay. And we saw before that is a sort of big O H convergence rate. So that's really nice. Okay, so now let's take a look at another one. So you can ask, so this is going to be Simpsons Rule. And you can ask, what about quadratic interpolation? Okay, so again, if we take a look at, say, we're going from A to B, and try and draw roughly the same function each time, we get this. So this is going to be, say, our f of x, and we want to compute the area underneath the integral. So we're taking a look at sort of our uniformly spaced points. And in this case, we want to interpolate 3 different points, say, each time. And so we're going to take an interval of like 2h whenever we're trying to compute this. So Simpsons rule is basically going to be the sum I equals, say, 0 to something, and then it's going to be f of I plus 4, f of I plus 1, plus f of I plus 2. And this is going to be times h over 3. And this is Simpsons rule. So this should be roughly the integral from a to b of f of x dx. Okay, so what do we see here? Really, so we're taking 2 at a time. So when we're incrementing from, say, the first one, which starts at 0, to the second one, it's going to end up shifting from I starting at 0 to I being at 2. So really, there should be a 2i and a 2i plus 1 and a 2i plus 2 to capture all 3 of those. And since we're going through this each time, we really also need to make sure that we stop when 2i plus 2 equals n, which means we're looking at when we have n minus 2 divided by 2 is the last I that we need to stop. So we stop here. Always have to work that out. All right, so there's going to be n minus 2 over 2 is when we stop. Okay, and yeah, I think that's good. Okay, so so that will end up giving us our formula, and you can go ahead and ask, so let me just label this. So this is the Simpsons rule. Okay, so Simpsons rule is pretty good. It actually converges at, I think, a big O of h to the 4. And what we can do is we can just take a look at each interval that we care about. So what we're going to be caring about is xi to xi plus 2, generally, of f of x dx. And, or, well, if you want 2i to 2i plus 2. And so then we're going to be comparing that there we go. So now we're going to be comparing that with this integral, x going from 2i to x 2i plus 2 of p2 of x, so a quadratic dx. Right, and at the end of the day, it's going to give us x2i, x2i plus 2. We're going to be looking at the remainder formula, x dx. Okay, so what is the remainder formula then? Well, for quadratic interpolation, r2 of x is going to be equal to, it's going to be f, the third derivative of, is that right? Yeah, third derivative xc, which depends on x, divided by 3 factorial, or 6. And now this is going to be multiplied by x minus x2i, x minus x2i plus 1, and x minus x2i plus 2. All right, and we're declaring that p2 of x2i is equal to f of 2i, p2 of x2i plus 1 is equal to f of 2i plus 1, and p3 of x2i plus 2 is equal to f of 2i plus 2. So we're looking at the, p2 of x. We're looking at the unique quadratic polynomial here, so interpolating polynomial here. Okay, and so now you can go ahead and integrate this and replace f triple prime. We're going to let m is equal to max of x in a b of f triple prime of x here, and ultimately the remainder formula you're going to get, just doing the same sort of thing that you did before. Then if you go ahead and compute the remainder formula, you can use the same sort of method and you'll get a really good result. It turns out that the Simpsons rule is even stronger than what you'd get by just using this remainder formula. It turns out that it, by happenstance, integrates away, it perfectly integrates every cubic polynomial, which means that it does better than just the quadratic that we were expecting here. So what it turns out that happens is that ultimately you get a stronger convergence bound, and I'll mention that later. Okay, but first let's go ahead and derive the formula. And so it's going to take some work, but it's the same sort of idea. So deriving the formula. Okay, so P2 of x is equal to f of 2i times x minus x2i or 2i plus 1 times x minus x of 2i plus 2 divided by xi minus x2i plus 1, x2i, and then x2i minus x2i plus 2, right? And then f of 2i plus 1, and this is getting really tedious, x2i, x minus x2i plus 2, divided by x of 2i plus 1 minus x of 2i, and then x minus 2i plus 1 minus x of 2i plus 2, and then plus f of 2i plus 2, then you have x minus x of 2i plus 2i, and then x minus x2i plus 1 divided by x 2i plus 2 minus x of 2i times x of 2i plus 2 minus x of 2i plus 1. Okay, so that's what we're working with. And I'll go ahead and do the first integral for you, and the rest I'll just tell you the results. And so it's the integral from x of 2i to x of 2i plus 2, because we're going over two these subintervals of this. So basically what we're looking for is we're saying that we're integrating x of 2i to x of 2i plus 2 of p2 of x dx, and this should be equal to f of 2i times the integral of x of 2i plus 2 of what we have there, plus f of 2i plus 1 times the other integral, plus f of 2i plus 2 times the other integral. And so we're looking for the numbers to put here, here, and here. And I sort of give you a hint at what they should be already. So if we take a look, we're going to have x minus x of 2i plus 1, x minus x of 2i plus 2, divided by x of 2i minus x of 2i plus 1, x of 2i minus x of 2i plus 2. Right, now in dx, we're going to make the assumption that x is equal to a plus t times h, just like before, which makes x of 2i plus 1 equal to a plus 2i plus 1 times h. X of 2i plus 2 is equal to a of plus 2i plus 2 times h, and x of 2i is equal to a plus 2i h, and then we have dx is equal to h dt, right? So we get h times the integral. Now it's going to go from 0 to 2 of t minus, this is again making it again the shift. I should probably do it one at a time, shouldn't I? All right, let's be honest here. So we got I going from integral from 2i to 2i plus 2 of t minus 2i plus 1 times t minus 2i plus 2 divided by, looks like that first term is going to be minus h, and the next one is a minus 2h, so we ultimately get 2h squared here, and we have h squared on top dx, or dt. And then shifting t to start at 2i, we end up getting this. We have h over 2, the h squares on top and bottom both cancel each other. We have an integral from 0 to 2 now of t minus 1 times t minus 2 and yeah, so that's dt. And yeah, so we can go ahead and calculate this out. So it's h over 2, integral from 0 to 2 of t squared minus 3t plus 2 dt. And this is h over 2 times the integral. Well, let's go ahead and start doing it. So the first one is going to be t cubed over 3. Putting in 2 in for t is going to give us 8. So that's 8 over 3. Next one is going to be 3 times t squared over 2. Putting in t equals 2 in there is going to give me 4 over 2. So that's just going to give me 2 times 3. That gives me 6. And then the last one is going to be 2 times t, and then that's going to give me 4, right? So we get for that. And putting that all together, h over 2. So let's see. I can go ahead and actually divide everything by 2. So it's going to be 4/3, and then it's going to be minus 1, right? And so it's going to be h over 3. Okay, cool. So what we end up getting then is this. We have the integral of x of 2i to x of 2i plus 2 of p2 of x dx. Thus far is f of 2i times h over 3. And what you're going to find next is going to be f of 2i plus 1 times 4h over 3. And the next one is going to be f of 2i plus 2 times h over 3. And you can work out each one of those. It's the same exact method. This was actually the hardest integral of the bunch. So yeah, so you can go ahead and work that out. Okay, so then I said before that we end up getting a really good error estimate using this, and we do. This will end up giving us h cubed, I think, altogether. Yeah, so this would tell us that it would give us sort of a h cubed after adding everything together. And if I was going to ask you to give some sort of proof on the exam, that I would just stop you there, because it's kind of some sort of highfalutin coincidence that this ends up working for cubic polynomials. And so, but let's take a look at what that means. So, so my claim is that Simpsons rule perfectly integrates cubics. Okay, so how do I mean by that? So I'm saying that if I take, say, the integral from, say, x of 2i to x of 2i plus 2 of, say, 1, for instance, then Simpsons rule should give a perfect answer for that back. And what Simpsons rule says here is that we should sample 1 at x 2i, x of 2i plus 1, and x of 2i plus 2, and so then and so this should give me the right answer. So the answer here should be h over 3 times 1. So we have 1 plus 4 plus 1, and let's see, what do we end up getting? That's going to be 6 over 3, so we get h times 2 And what is the actual answer here? Well, it's going to be 1 times x of 2I plus 2 minus x of 2I, and indeed that is 2h. So check, it integrates that precisely. We could check again for the integral of x of 2I to x of 2I plus 2 of just x dx. And what is this? Well, this is going to be x squared evaluated at x of 2I and x of 2I plus 2 divided by 2. And let's see, so we're going to have x of 2I plus 2 quantity squared divided by 2 minus x of 2I squared divided by 2. And we can simplify this a little bit. We have x of 2I plus 2 minus x of 2I times x of 2I plus 2 plus x of 2I divided by 2. And this is going to give me, looks like it's going to be 2h times x of 2I plus, sorry, it's going to be 2x of 2I plus 2h over 2. Where I'm just writing this as x of 2I plus 2h. Right, and so this gives me 2h times x of 2I plus h. Right, I don't know if that's going to end up working out cleanly, but let's go ahead and see if that's what I end up getting. Okay, so if I take a look at yeah, let's see. So if I go ahead and take a look at this, I'm trying to sample, so we were wondering if that equaled that, sorry, cleaning up. So we're asking if this is equal to h over 3 and f2i plus 4 times f of 2i plus 1 plus f of 2i plus 2, right? So if I just sample x at each of these points, it's going to be x of 2i plus 4 times x of 2i plus 1 plus x of 2i plus 2. And let's see what we end up getting. All right, let's see. So what I can do is I can actually write each of these in terms of x of 2i. So this is x of 2i plus h. This is x of 2i plus 2h here and here. So I get h over 3. I have x of 2i, but I have several contributions. So I have one contribution here and one contribution here, so that's 2, and then I have 4 from this guy, so that's going to be 6 times 2i. And let's see, and then I'm going to have, as far as my h's go, I'm going to have 4 h's from this guy, and I'm going to have 2 h's from this guy, and so that's going to be 6h there. And so ultimately I get, let's see, it's going to be 2 times h times x of 2i plus h, and ta-da, check. So it exactly integrates linear functions. So if your function was just a linear function, Simpsons Rule so far will give you an exact reproduction of it with no errors. And same if it was just a constant function. And so we can keep this going, and we have integral from x squared of xi, x2i to x of 2i plus 1, and dx, and we can go ahead and integrate that. It's going to be x cubed over 3 of x2i, x of 2i plus 1, and so it's going to be x of 2i plus 1 cubed divided by 3 minus x of 2i cubed divided by 3, and this is x of 2i plus, sorry, it should be a 2 here, 2 here, there should be 2 here, plus 2h cubed minus x of 2i cubed, all this divided by 3. And so if you want, we can factor that. And so it's going to give us x of 2i plus 2h minus x of 2i times, well, let's see, if we were writing x cubed minus y cubed. What does this give us? It would be x minus y times x squared plus xy plus y squared, right? And then, yeah, so you get x of 2i plus 2h, this guy squared, plus x of 2i plus 2h times x of 2i, and then x of sub 2i squared, all that times this. And you can keep going through, and so then, you know, if you want for your homework, you can show that this is exactly x of 2i plus 4 x of 2i plus h squared and squared plus x of 2i plus 2, yeah, let's just say x of 2i plus 1 squared, and this times h over 3. And that'll work. And ditto for the integral from xi x of 2i to x of 2i plus 2 of x cubed dx. Okay, so so it exactly reproduces all of those formulas. And so if you were to instead write f using its Taylor remainder after 4 Taylor components, xi, so let's maybe change colors here. So what you're going to get is you're going to have x of 2i, x of 2i plus 2 of f of x dx minus the integral of x of 2i plus 2 of p2 of x dx. What you end up getting is that if we write x of 2i plus 2 and f, say f of you know, just write out the third order Taylor polynomial t3 of x plus whatever that remainder is, t3 r3 of x, minus p2 of x dx. That Taylor polynomial is going to be completely determined under the integral sign by the interpolation. So this ultimately is equal to just the integral of x of 2i plus 2 of r3 of x dx. And we have r3 of x dx is going to be f to the fourth derivative xc, which depends on x, divided by 4 factorial times h to the fourth power. And this times x, yeah, well, sorry, not just h to the fourth power, but x minus x2i to the fourth power. Right, and so when you integrate this, it's going to end up giving you sort of something as sort of h to the fifth times some constant times h to the fifth power, and then adding all the intervals gives you something as big of h to the fourth power. And so that is Simpsons Rule, more or less. So Simpsons Rule works out to be a really high power of convergence, and that ultimate remainder that you end up getting, just it's a little bit too much to work out here. Let's see. So this ends up being h to the fifth So it's gonna be, sorry, the overall thing is gonna be h to the fourth divided by 90 times the maximum value that you get here, c. So this is what we've been calling m. So it's the maximum of the fourth derivative. So it ends up converging really, really fast. And so before we were thinking it would, going from a linear interpolation to a quadratic interpolation would only get us from being sort of big O of h squared to big O of h cubed, but it turns out that Simpsons Rule does even better. And so that's a really nice result. In any case, but if I was going to ask you to prove, say, the convergence rate for Simpsons Rule is just sort of being big O of h to the 3, I would really just want you to integrate this rather than using the sort of lucky thing that it integrates all cubic polynomials. So maybe this would be a good place to stop.
Okay, so welcome back. So now you have like a small little toolbox to do calculus. We know how to take numerical derivatives, and we know how to take numerical integrals. We have several ways of taking each of them, and we know how to get better and better differentiation formulas if we want, assuming we have higher and higher differentiability. But you can use Newton's interpolating formula in order to get all sorts of different convergence rates. And same is true for integration. You could keep adding more points, concatenating more and more of your subintervals and using higher and higher interpolation there. And that will indeed give you a higher rate of convergence. But after a certain point, your data is only so good. And so, I mean, like, if you're already getting fourth order convergence out of Simpsons Rule, it doesn't necessarily make a whole lot of sense to even try to go higher than that. But you could try. I mean, like, you might have a really good situation and perfect data, and you could get conceivably better convergence results. But, if you just need something to throw at it, I mean, having Trapezoid Rule and Simpsons Rule are two really good general purpose integration routines. And so, provided you have a continuous function. If you have discontinuities, then you're going to need to use some sort of weighted integration routines, and that's what we're going to talk about next. In any case, thanks for listening, and yeah, I'll see you later.